Alright, so the major way that we're going to get around having to use that nasty integral to figure out what the electric field is at some point P is using Gauss's law. And to set up Gauss's law, we need to start by talking about the electric flux. So before we worry about electric flux, let's talk about something that probably has a little more, we have a little bit more feel for on just a day-to-day basis. So let's define the air flux to be a measure of how much air flows through a window. So basically the idea is simple. You open up a window, you stand there in front of the window, you feel some amount of air flowing through the window. So that air flux is going to depend on three things. First thing is how windy it is. So the arrows here are representing the flow of air, and so this is going to be a particularly windy. Right, I've got a lot of arrows. They're all very long. Less windy would mean, well, I got fewer arrows coming through, right? So in some sense, how much air comes through my window, that's going to tell me about how windy it is. Second thing is the size of the window. Obviously, I'll get a very different value for the air flux if I use a large window than if I use a smaller one, right? So there's clearly plenty of the air that before was able to get through the window that can't now because I'm simply using a smaller window. And then the third thing it depends on is the direction that the wind is blowing. So you'll notice here that the wind is basically blowing perpendicular to the surface of the window. I could imagine a situation in which basically the wind was blowing straight up the wall, and then I would get very little air coming through rather than a lot of air coming through. So these are the three things that air flux depends on, and what we'll see is electric flux is pretty much going to work exactly the same way. So electric flux is a measure of how much an electric field flows through a particular surface. So another way that we'll talk about this is how much do your electric field lines pierce your surface. That's what the electric flux is trying to tell you. And again, it depends on three things. So you'll notice here's some simple area here. I've got an electric field in orange. And so there's three things that the electric flux is going to depend on. One's the strength of the electric field. I know that the strength of the electric field basically tells me how clumped together these arrows are. If I have a very weak electric field, I don't have very many arrows. If I have a very strong electric field, I've got a lot of arrows drawn. So clearly the stronger the electric field, the more electric field lines will pierce my surface. The area of the surface, again, in the same way we talked about with the window, if I have a very small surface that doesn't have the opportunity to catch a lot of electric field lines. If I have a very large surface, that's obviously going to be pierced by more electric field lines. And then third is the relative orientation of the electric field in the surface. Again, you'll notice here that my surface is basically perpendicular to the electric field lines, which is going to maximize the ability of the electric field lines to pierce the surface. So the electric flux, just the same way we talked about with the air flux, depends on basically the same three things. The strength of the electric field, the area of the surface the electric field is piercing, and then the relative orientation between those things. And so in its simplest form, I can sort of take care of all three of these parameters by calculating the electric flux through for a constant field through a flat surface in the following way. It's simply going to be the dot product of the electric field vector with the area vector. So a couple things here. One, we're saying we've got a constant field. So this electric field vector, again, you can notice these lines, they all point the same direction, so they're all evenly spaced. So here's my constant electric field. And then what's the area vector? Well, basically the area vector, it has a magnitude that's equal to the area of your surface. So again, the larger you make this surface, the longer you're going to make the magnitude of your area vector. And then the direction of the area vector is normal to the surface. So basically the area vector is perpendicular to your surface. So to maximize the electric flux, what I want to do is I want to line up the area vector with the electric field vectors. And so as a dot product, right, I know that this is one way to calculate this is just it's the x component of the electric field times the x component of my area plus the y component of the electric field times the y component of my area plus the z component of my electric field times the z component of my area. So that's just our definition for how we calculate a dot product. The other way that we can do it is, again, it's the magnitude of the electric field times the magnitude of the area times the cosine of the angle between them. And you'll notice that these three things happen to be exactly the three parameters we were talking about before. The strength of the electric field, the area of the surface that the electric field is piercing, and then my cosine theta gives me some indication of the relative orientation between those two vectors. All right, so theta here is very clearly defined to be the relative angle between the area vector and the electric field vector. All right, so a few more things to think about with electric flux. So again, let's come back to sort of our easiest equation to interpret. We got EA cosine theta is going to give me the magnitude of the electric flux. And so a couple things. One is, what's the unit? Well, obviously this has to have units of the electric field times units of area times units of cosine theta. Well, cosine theta is just a number, so that's unitless. Units of electric field are newtons per coulomb. That's one unit I have. Units of area are meters squared in SI. And so the electric flux units have got to be Newton meters squared per coulomb. And then this equation is really sort of highlighting that there are three ways that I can change the electric flux through a surface. So first, change the strength of the electric field. Basically, change this component. Second, change the area of my surface. Change this component. And then the third one is I can change the relative orientation of the electric field in the surface. So you'll notice that if I want to maximize the electric flux, then that means I want to make cosine be as large as it can be. Cosine, the largest value cosine can take is 1. That happens when theta is 0. And theta being 0 means that my electric field vector and my area vector point in the same direction. So I maximize the flux. The maximum flux occurs when the surface is perpendicular to the direction of the electric field, so that the normal to the surface, which is the direction the area vector points, is parallel to the electric field. So that's how I get the maximum flux. The minimum flux I can get is 0, and that happens when the electric field is perpendicular to the area vector. So that's a situation where the electric field and the surface are basically running parallel to each other. So we just got to keep in mind what it is that we actually care, what it is that this cosine theta cares about, and it cares about the angle between the electric field vector and the area vector, and that area vector again is perpendicular to the area, to our surface.